So we saw before that if I have a carboxylic acid, I use thionyl chloride to make that into an acid chloride, right? So thionyl chloride used to convert carboxylic acid into an acid chloride in a mechanism that we saw in the last section. So just like the analogous alcohol reactions, we can also use PBr3 here to prepare the acid bromide. So here's an acid bromide, technically similar reactivity to an acid chloride, although acid chlorides really are much more common. Let's just remind ourselves of the intermediate that forms here. Remember, the thionyl chloride, the sulfur adds actually to the carbonyl carbon. So our intermediate is our COS double bond OCl. Okay, and then back to the carbon, the original OH of the carboxylic acid is a carbonyl. No. So this is the leaving group, right? So when chloride attacks that, we get addition to the carbonyl, and then it kicks out the leaving group. Okay. So that's how acid chlorides are formed. Acid bromides are formed in a very similar manner. The carbonyl carbon adds to the phosphorus. Okay. So we end up with R. See, right? The OH becomes a new carbonyl here. I have O, then PBr2, which is now OPBr2 is a good leaving group. So bromide adds to the carbonyl to make an acid bromide. So essentially that thionyl chloride makes a good leaving group that a halide can come in and displace. So acid halides, they're the most reactive of all of the carboxylic acid derivatives that we'll have in this chapter, so we can very easily convert them into any of the other carboxylic acids just by a direct addition of an appropriate nucleophile. So if we can identify a nucleophile to replace the halogen leaving group, it'll pretty much work with this. So water nucleophile makes a carboxylic acid. A carboxylate, right, CO2 minus, makes an anhydride, right, because that's what was added in each case, right? An alcohol nucleophile makes an ester. Amine makes an amide. A hydride nucleophile can make an aldehyde. A second addition makes a primary alcohol. We can get a tertiary alcohol by 2 additions of a Grignard reagent. I'll show you a Gilman reagent that can make a ketone out of it. Here, let's write that R2CuLi makes a ketone, RC double bond O, different R, let's call that R prime, and then reduction of that can make a secondary alcohol. So HR prime. There's that primary, secondary, tertiary that I was talking about, that synthetically we have access to any of those alcohols. These are all downhill energetic reactions. Okay? So they all occur spontaneously, which means we don't need forcing conditions. That means we typically get pretty good yields without much side reactions. So let's quickly go through, since we don't need to dwell on this too much, since the mechanism now is familiar. It's a nucleophile adding, kicking out the halogen leaving group, right? And we'll be talking about chlorides here from now on. So all we have to do is add water to an acid chloride, right? Our tetrahedral intermediate is water added in an O minus. The O minus comes back down, kicks out the chloride. We then remove the proton, right, from the water that added, just to make the compound neutral again, and we get a carboxylic acid. Acid chlorides are reactive enough that we don't need any additional activation for a neutral nucleophile to add. So just plain old regular neutral nucleophiles can add to that very reactive acid chloride. Now, if we look here, we kicked out a chloride. We also removed an H. So HCl is produced as a side product of this reaction. And if you look at the reactants, you can trace that, right? We had a chlorine that doesn't appear in the product. We also have one of the H's that doesn't appear in the product in the water there. So HCl is produced. So we usually run this reaction with a weak base, something like pyridine. So pyridine, or I usually PY, it's benzene with a nitrogen in it, right? Directly in the ring. So that nitrogen is a weak base, so that any HCl that's produced makes the pyridinium chloride salt. So we end up with NH as a plus charge with chloride as a minus. So pyridine captures HCl. And that's important to do. We don't want this reaction to get too acidic. Hydronium, right here, for instance, is no longer a nucleophile. We have to have neutral water to do that. We can make anhydrides very efficiently. This right here is actually the best method for making anhydrides. Right? Most general, any anhydride can be made this way. We start with a carboxylate ion. So if I wanted to do acetic formic anhydride, it actually doesn't matter which one we use for which. I'll take one of them and deprotonate it, right? So if I had formic acid, HC double bond O, OH, I could react that with sodium hydroxide to make sodium formate plus water, but there we've deprotonated. Right, sodium hydroxide is a strong enough base to deprotonate carboxylic acids. If I add that to an appropriate acid chloride, you can imagine what happens. The O minus adds to the carbonyl, and then chloride is expelled as a leaving group. So here formate has added, and we have an anhydride. So the O minus of the formate becomes the O between the two carbonyls in the anhydride. And it works pretty well. Actually, the most efficient method for production of esters, really the most general way to make an ester, is with an alcohol adding to an acid chloride. So if I have benzoyl chloride and cyclohexanol, you can guess what happens here. The lone pairs on the oxygen are the nucleophile. They add to the carbonyl. That kicks out the chloride leaving group, and after a proton transfer, right, because look at what happens here. I would have to get rid of the H from the alcohol that added. We also have chlorine that was expelled, so we don't want to collect up HCl in here. So again, we use pyridine to sop up all that extra HCl that's produced. Extra HCl could possibly protonate this alcohol, rendering it no longer nucleophilic. So really any reaction where we expel a chloride and have to remove a proton, we do that reaction with pyridine present to take care of that HCl. This reaction, like I said, is very general. Unhindered alcohols tend to react faster, but this right here is a secondary alcohol, right? 2 R groups on the alcohol carbon. And this reaction, look, it's got great yield. It's probably not fast, but energetically it's downhill, and it really works pretty well. So this is the all-purpose general method for making an ester. It does require an acid chloride, and acid chlorides are really not pleasant to work with. They smell awful, and they're so reactive you have to be very careful to keep water out of any of the reaction mixer, so it has to be done under an inert atmosphere, totally sealed off from any water vapor. We can make acid halides into amides. Very simple. This is the best method for producing amides, right? You're noticing the theme here with acid chlorides. We can very easily make them into any of these other carboxylic acid derivatives. So just a neutral amine displaces the chloride, making an amide. We use 2 equivalents of the amine to capture the HCl, right? Because NH3 becomes a C double bond O NH2, so we had to remove a proton. So let's just use another equivalent of that base to sequester HCl as an ammonium chloride salt. Okay? So same thing happens here, right? The nitrogen is the nucleophile, the chlorine is the leaving group, and it's just a simple substitution that happens in 2 steps. If our amine is expensive, like in this case, here's morpholine, and we don't want to use 2 equivalents of it, we could just use sodium hydroxide. That's fine. Sodium hydroxide is not going to deprotonate anything in here. It's not strong enough, but any HCl produced will instantly be neutralized by that sodium hydroxide. So look at this here. If you're deciding what's going to do the reacting, right? Nitrogen has a lone pair, but there's also this oxygen in the molecule that has a lone pair. Nitrogen is a stronger nucleophile than oxygen is. Okay? Oxygen's electronegative, so it has a little more of a partial minus charge, but since it's electronegative, it's able to hang on to that negative charge a little better. Okay? Nitrogen's lone pairs are more available for attacking, right? Since nitrogen is not quite as electronegative as oxygen. So that's why it's the nitrogen in this compound that is the nucleophile, not the oxygen. Chlorine, of course, in the acid chloride is the leaving group. The reason that having base present with this one is so important, right, just like we've mentioned, is that if I have an amine like this, like RNH2, that I want to be acting as the nucleophile, but if I have HCl present from the other reactions that are happening nearby, amines get protonated. Right? We get RNH3 plus. We no longer have a lone pair on that nitrogen, so this is not a nucleophile. So that HCl that's produced will render our amine no longer nucleophilic. Right? It'll just completely take it out of commission for any additional reaction. So that's why we either need 2 equivalents of this, one to do the reaction and the other to react with the HCl, or if I add some sort of base here, like hydroxide, we can pretty easily get rid of that HCl. Other reactions, acid halides can accept hydride reagents, right, as a reduction. That makes for primary alcohols. You can imagine the intermediate that we have here, right, because hydride is H minus. As right here comes up, okay. Chlorine acts as a leaving group in the second step, so our intermediate is an aldehyde, pH C double bond O H. Okay. But again, lithium aluminum hydride is a powerful enough nucleophile that it adds to that aldehyde again, giving a second equivalent, right, of hydrogen added, and that's how we get this primary alcohol. So once again, lithium aluminum hydride reduces all of these derivatives to make primary alcohols. Grignard reagents behave pretty much identically, except it's R groups that we're adding instead of hydrogens. So we cause 2 R groups to be added. It'll make a tertiary alcohol via a ketone intermediate. So let's make sure we're clear on this mechanism. A Grignard reagent like this methyl magnesium bromide has a C minus there. That adds right there. Chloride is the leaving group. So here's our ketone intermediate, which the Grignard reagent, which a second equivalent of Grignard reagent will add to again. This time there's no leaving group. That chloride here is the leaving group. No leaving group, so we're stuck there. We have an alkoxide which protonates to get an alcohol. So we've added these 2 R groups to make a tertiary alcohol. If you're doing this retrosynthetically, just find the 2 equivalent R groups on that tertiary alcohol. Okay? So if you have a tertiary alcohol you need to make, if there are 2 equivalent R groups on there, make that from an acid chloride and add 2 equivalents of Grignard to it. Now, notice the Grignard reagent, let's show you this here. The Grignard reagent very easily added to this ketone intermediate, so we can't stop at a ketone with Grignard. Even if we tried to just do one equivalent, we'd end up with a mixture of products. Okay? If instead I use a milder carbon nucleophile, like a Gilman reagent, okay, once again, this is our less reactive, okay, our less nucleophilic carbon nucleophile. What we can do, we can add this Gilman reagent, and the acid chloride is really the only carbonyl that a Gilman reagent can add to. It's a lithium dialkyl copper, so R2CuLi. So it might look something like CH3 parentheses 2 CuLi, for instance. Okay, so the intermediate, we haven't seen this before, but it's actually a copper that adds to the carbonyl, right, displacing the chloride, and that's an intermediate that actually spontaneously rearranges. Okay, so the carbon sort of attacks this R group and rearranges to spit out the copper. It's sort of a complicated organometallic mechanism that we don't worry too much about in this course. But this copper nucleophile is not a very strong nucleophile. Okay? The acid halide is the only carbonyl that a Gilman reagent adds directly to. So that's why the ketone that we have left, we're done. Okay? The Gilman reagent is not powerful enough to add to a ketone. Take a look at this reaction here, which, if we're careful about having one equivalent of this Gilman reagent, it essentially just substitutes for the chlorine, and we end up with the ketone right there, and that's it. It actually acts like other neutral nucleophiles, like when we made esters or amides from acid chlorides. Right? The resulting ketone is no longer reactive to neutral type nucleophiles. But notice this is also an alpha beta unsaturated compound. So we've made an alpha beta unsaturated ketone as a product. And we actually get that if I carefully add one equivalent. This is the carbonyl carbon with the chlorine on it is the most reactive site here. But if I used an excess of the Gilman reagent, we would take the alpha beta unsaturated ketone, and recall that Gilman reagents can undergo 1,4 additions. They never add directly to a carbonyl, but they can add to the beta carbon. So remember what happens in a 1,4 addition. Double bond migrates over, you protonate the OH, so you have an enol, but that tautomerizes into a keto form. So what we get is CH3, CH2, CH, CH3, CH, and then here's our ethyl group from the Gilman reagent on the beta carbon. All right, alpha carbon is next to it. That has a CH3, and then the same ketone as we had before. So this tells us about reactivities here. If I have an acid chloride, that's the most powerful electrophile in the molecule, right? Because that chlorine pulls electron density out of that carbon. So Gilman reagent adds once to that. Okay? Once that reaction is finished, if I have more Gilman reagent, I can do a 1,4 conjugate addition, right, at the beta carbon. So that removes the double bond. We have a new H there on the alpha carbon. So look back at our ketone aldehyde chapter to review that if you need to.